here we are discussing one more concept related to rotational motion, the theorem of parallel axis. Again, to save time, I have written down the statement or the explanation for what is the theorem of parallel axis. We will go to that a little later. Let me begin by drawing a diagram and giving you a background upon theorem of parallel axis. And so let us again say we have an object. Let us say this is an object of mass m, and let us say this is the center of mass of the object C, and there is an axis passing through this, right? And this axis we are denoting by x dash. This is the axis passing through the center of mass, okay? And we know that if this is the axis passing through the center of mass, then the moment of inertia, right, ICM, that is the moment of inertia about the axis passing through the center of mass, ICM, is given by sigma m r square, where m is the mass of each and every particle of this object and r is the distance of each and every particle from the axis of rotation, right? So this is something which we have already studied earlier. The question is that if we want to find out the moment of inertia of the same object about any other axis apart from x dash, let us say an axis over here, let us say axis passing through this particular point, right? Such that the distance between these two axes is a. This axis is of course parallel to this and at a distance a. So if I want to find out the moment of inertia of the same object of mass m about this axis, then how do I find that out? And the theorem of parallel axis helps us give this equation. What it says is that for a body of mass m, let the moment of inertia about the axis passing through the center of mass, that is x dash, be ICM. Then the moment of inertia about any other axis which is parallel to x dash, and any other axis which is parallel to x dash and at a perpendicular distance a from x dash. This distance between the two axes, the shortest distance is a. It is given by I is equal to ICM. So the moment of inertia about this axis I is ICM, which is sigma m r square plus m a square, where m is the total mass of the body and a we know is the distance between the two axes. So this theorem helps us find out the moment of inertia of an object about any other axis apart from the axis passing through the center of mass. So let us try to see how this equation has arrived. So what we'll do is let us say we take a point. Let us say this is a point. Let us say this is a point P, and let us say it is at a distance r from the axis x dash, that is the axis passing through the center of mass. Right? Now, the moment of inertia about the point P about this axis, let us call this, what shall I call it? Let us call this axis AB. Right? So, IAB, right? The moment of inertia of this particular mass, which will be of mass small m, about this axis will be, so I'll write over here, moment of inertia about axis AB, right, of the particle P. Right? In fact, I should have written moment of inertia of particle P about axis AB, right, would be m r plus a whole square. Let me write over here m into r plus a whole square, because m is the mass of the particle and the distance from this axis is r plus a whole square. Right? So if I want to find out the moment of inertia of the entire body about this axis, it will be I AB, or simply I is equal to sigma of m r plus a whole square, because the masses of all the particles is m, and for each particle I'll take the distance r, right, from this axis. A is of course constant a. And if I open this up, I'll get sigma m into r square plus a square plus 2 ra, and this will be equal to sigma m r square plus m a square plus 2m ra. And in in this case, since A is constant, right, I can remove A from this sigma sign, so I'll get A into sigma of mr square plus, I can take that out, so ma plus 2 m. Okay, so this is how I get as the equation for moment of inertia about this particular axis. Right. Now, before I solve this, I maybe will need to revise a concept which you would have studied in an earlier class, the principle of moments. Right. Right. And the principle of moments it says that for a body in rotational equilibrium, right, the sum of all torques acting on it is 0. In fact, I should say the algebraic sum. The algebraic sum of all torques is 0. That means sigma tau is equal to 0. Right? Now, if you have a body on which there are no external torques, supposing this is in a body on which there are no external torques, there is no external torque acting on it, on this body, then the torque acting on this body would only be because of its particles, right? Each particle mass m, right? Let us say this is the axis of rotation, right? The torque acting on this body would be because of these particles, because of their weight acting in the downward direction, mg, right? And if this is in rotational equilibrium, that means it is not going up in this direction, or is not rotating in this direction, or in this direction, or not moving up and down, then sigma tau is equal to 0, and torque is m, mass of a particle, and its distance r. So if sigma tau is 0 for a body in rotational equilibrium, that means sigma mr is 0, because tau is mr, because this is tau is force into r, and in this case the force is the weight mg, right? And we could write sigma mgr is equal to 0, but g is a constant, so I write sigma mr is equal to 0. So this is something which we'll be using over here, therefore I thought I'll just refer it over here, right? Coming back to this, I is equal to, now I have taken a out of the equation, right? So I'll get sigma mr square plus ma square plus 2mr. Now if I look at each one of them individually, right, what will I get? I should get sigma m. If I just write this down over here, in fact I have made an error over here. Let me redo this step over here. Let me rewrite over here. So sigma, in this case m is common, so I can take out m out of the equation, not a. M should be taken out. So m r square plus a square plus 2ra, and therefore I'll get sigma mr square as plus sigma ma square plus sigma 2mra, right? Now if I look, what is sigma mr square? Sigma mr square is ICM, so this is something which I'll get ICM plus sigma, over here we have sigma ma square. Now as far as sigma a square is concerned, I can write this as a square into sigma m plus, right, a into sigma, or 2a into sigma mr is equal to ICM plus sigma m. Sigma m would be the total mass of the entire body, because this would be addition of the masses of each and every particle. So m, total mass of the body, plus 2a. Sigma mr, as we saw over here, is 0 because this body is in rotational equilibrium. So this will be equal to 0, and therefore this term will turn out to be 0, and therefore I get I is equal to ICM plus ma square. So this is how the theorem of parallel axis helps us find out the moment of inertia of a body from about an axis apart from the axis passing through the center of mass.